It is fun. I had to go look up Biot-Savart law to try to figure out what these currents would do. It was shameful. I didn't remember any of it. B equals U dot. IDL cross R over R cubed. How do I do a cross product? Okay, so let's first talk about the spacecraft. Primarily, the fluctuations will come from the inherent flux in the solar radiation pressure, and then thruster noise. The solar wind and micrometeorites are much less by comparison. I'm not even going to talk about them. I said earlier the relative fluctuations in the solar flux are about 0.1% at a millihertz. They get much worse at about, well, as 1 over nu to the 1/3 power. So we already talked about this in the reality check. The solar radiation pressure fluctuations on the spacecraft are down there at about 10 to the minus 10 meters per second squared. The thrusters are a little bit worse, maybe twice as bad. So the net, when you RSS them, the net contribution from spacecraft thrusters is 3 times 10 to the minus 10 times this factor. Not only is it the dimensionless coupling to the spacecraft, but it's also helped out by a gain of the spacecraft. Where we said earlier that K needs to be smaller than about 10 to the minus 7 per second squared. That tells me that if I want to make this contribution, remember what, that's this contribution. If I want to make it smaller than, say, maybe 10% of the whole budget, I need a spacecraft gain, control loop gain of about 3,000, which nobody rolls their eyes at, not so hard. So see, we've already made a bunch of predictions based just on the spacecraft. But now the big deal is to get to that first term, and this has about 15 contributions, and one of the worst ones at very low frequency, was only discovered last December. So this is science in progress, and this is why it would really be a good thing if you would go through and check the critical things on the table of 15 components, because if we could just find one that just about kills us, and we only found it last December, well, who knows what else is in there? Either ghosts are lurking, or we've done something wrong. So there, and don't worry about this. This is just for your reference if Kip really makes you do these problems. There are about 15 contributions. 4 of them are magnetic, and they come primarily from gradients of the local spacecraft magnetic field, and also fluctuations in the interplanetary magnetic field. And of course, they depend on the velocity of the proof mass in spacecraft, the charge buildup, and susceptibility. Then we've got about 3 that are just simple classical mechanics impact forces. Cosmic rays, mostly 200 MeV and higher, residual gas, and laser photon radiation pressure. And then there are another 3 that are entirely thermally related, and one of them at least is just a killer. The killer is really the thermal radiation pressure difference on each side. But you also have a so-called radiometer effect, which is temperature fluctuations means differential gas pressure on each side. So in addition to mechanical collisions of gas, you have differential gas pressure because of thermal fluctuations. And then, of course, the other one I talked about was because of temperature fluctuations on the spacecraft, you have thermal distortions of massive elements, and that mimics a gravitational wave. And then you got 11, 12, 13, 5. 5 that are from this capacitive sensor. And 2 of them, one in particular, the one we found last December, just blows the budget completely if you try to take it down to 10 to the minus 5 hertz. I mean, it blows it by a factor of 8. Instead of 3 times 10 to the minus 15, it takes a whopping 9 all by itself. So strong impetus to look at it carefully and also to consider other options for the sensor or find ways to move them.
So let's just remark, going down 10 to the minus 5 hertz means wanting to be able to study very massive black hole binaries.
That would be the thing, and then risking that when it comes to binaries, you're in the noise.
And so you're only going to guarantee us spacecraft, or at least a performance down to 10 to the minus 4 hertz, and we have to pray to be able to go to 10 to the minus 5.
You will, but the curve goes up so steeply. All these effects that you're seeing that make the force noise not white. All these things that the fluctuations in charge, the fluctuations in interplanetary magnetic field, the fluctuations in the solar flux, they all have this 1 over nu or 1 over nu to the 1/3 or something, and that just really kills you down.
So this lovely left edge of the noise curve that we see is going to skyrocket over 10 to the minus 4.
Yes, and instead of going like that, it starts to curve up like this.
But if you switch to some other readout and actuation system, then maybe you can do better for us.
All the electrostatic forces would go, and the only one that would remain bad, but it's still a factor of 3.5 below the total budget, is the thermal pressure. And if you want to get down to 10 to minus 5 hertz, these long period thermal fluctuations, they start to require active thermal control, but not difficult. We're talking about active thermal control of the spacecraft and the wide tubes, not the proof mass. But it's really not something scary, not something that even hasn't been done. But it would be needed, and so it's an added expense. Again, this table is, you can just use it for homework and reference. Here's your 15 disturbances that we know of now to the proof mass. These 5 are from the capacitive sensor. Here's the one that bites you down here at 10 to minus 5 hertz. It just destroys the whole budget. And it comes from charge fluctuations on the proof mass multiplied by the unavoidable difference in voltage across the 2 plates, which you have to sense. The charge, here. But the charge fluctuations we also can't help. That's just from the random impacts of the cosmic rays. So we don't, and those random impacts go as 1 over nu. So we're stuck here. This is a killer at low frequencies. Other than that, at a millihertz, for example, the capacitive sensor isn't all that bad. Although there's some assumptions here to make it look not bad, like a capacitance to ground that's very small, which may not be true. So this factor of 1/6 may not be there. This could be 6 times higher, which would be bad. There are lots of reasons why to believe that these numbers could be much worse than I've written. These numbers, however, are not terribly debatable. So, number 1, the fact that these are bad, and number 2, the fact that they're debatable, means that a lot of work needs to be done looking at the sensors and other options. The fact that these are bad in some cases, but not so debatable, just means that we need to look at what causes them to be bad and see if we can't work on it. For example, here's something, a magnetic effect, I'll talk about in just a minute, that depends primarily on fluctuations in the interplanetary magnetic field, and of course requires a small susceptibility for the proof mass. We can't do anything about the fluctuations in the interplanetary field, but here's a gradient, B over R, of the local spacecraft magnetic field. Since that becomes an important factor at the low frequency, there's impetus to drive down the local spacecraft magnetic field. All that means is perhaps push the electronics and the power where the currents are, push them out a little farther. That doesn't seem so difficult. Other things like residual gas pressure, they don't have any frequency dependence. The thermal radiation pressure fluctuations, they're bad, but they never get worse. And they're livable. So, anyway, you can use that table for Kip's problem. Very briefly, it looks like a lot, and it is a lot. I'm not going to go through it much, but you'll have it for reference. The magnetic field, I've had questions before from people who go, why is magnetic such a big deal? And they can understand the Lorentz force. Let me go back to this Lorentz force because it's really not that big a deal. You have to go down to 10 to the minus 5 hertz before the Lorentz force is that big a deal. And that's because we don't let the charge build up that much. We'll discharge the proof mass maybe once a week, maybe only once every 2 weeks. And this still wouldn't be a bad factor. So the Lorentz force is easy to understand, but it's not the one that bites you. The one that does is the one that's not intuitive, which comes purely from the susceptibility of the proof mass, the local magnetic field, and unavoidable fluctuations in the interplanetary field. So that,
you're assuming the local magnetic field is really pretty steady, and the dominant fluctuations are due to the interplanetary.
I assumed fluctuations for it, and I assumed them to be, I think, about 10%. Yeah, at worst. But they're much less than the interplanetary fluctuations. The problem is that the interplanetary fluctuations have a 1 over f frequency dependence. The spacecraft magnetic field fluctuations do not. So at a millihertz, the spacecraft fluctuations are bigger, but they're livable. But when you go down in frequency, they don't change, and so they remain livable, and the interplanetary fluctuations dominate. So that's about. The local field, which we will eventually have to drive down, comes from magnets on the laser. I mentioned that. And you guys can check this little calculation. I said, okay, maybe an average magnetic moment of 1.5 ampere meter squared if I put the magnets at 35 centimeters from the proof mass, and I get about 7 microtesla. The other one, come on, you guys got to work this out just because I had to do it. And I had a hard time remembering it. So just imagine two current, maybe 20 amps flowing in a circle about half a meter away, and the other one 2 millimeters away from that going the other direction. And tell me what the field is about a quarter of a meter away, and I get about 20 nanotesla. So I get a total magnetic field in the spacecraft.
Is that a reasonable current to expect?
Yeah, that's what tell me. You check it. I think so. Anyway, I thought it was about a worst case. And it still gave me something smaller than the magnets I can't get rid of for the lasers. Okay. It's a lot, but it's still smaller. This is the killer. So the question is, can you put them farther away? Anyway, you might consider other ways to reduce it. Now, so the proof mass, in the presence of both these fields, the local field and the interplanetary field, develops a magnetic moment. And the force, come on, you guys get to do this physics. The force is like the gradient of both of them, but the dominant one will come from fluctuations in the interplanetary, and that's this guy. So it's 1/100th of the total budget at a millihertz, but it becomes almost the entire budget at 10 to the minus 5 hertz. That's 4 of 15. Now we come to the impact, classical mechanics, and there's only one that's really important, but you can follow the physics. And I'd really appreciate it if you would check all these things, because if you find something that's worse, we want to know about it. I took cosmic rays, and I said that they're really not going to matter to me unless they're more than about 200 MeV. Okay. Now the only data I had said they arrive at maybe 30 per second. And when they go to charge the proof mass, I just said they charged it equally, plus and minus, but that's not clear either. There's probably better data than I used for that. Anyway, acceleration seemed to be negligible. Residual gas, on the other hand, most of which is nitrogen, you can take its average velocity, 3/2 kT. I get about 15, 16 meters per second. So they're going to give an average impact rate. Check all these, but I think they're right. Maybe not, but they look right. And I assumed random Poisson statistics, so the fluctuation in the impact rate is like the square root of the rate. And I get about 10% of our whole budget, a little bit less. And that's only if I assume a very small local pressure. It's not that sensitive to pressure, it's the square root of pressure. Nevertheless, I had to make that assumption to make it that small.
So these nitrogen molecules are from outgassing from the spacecraft?
That's what brings the final pressure.
And how reliable are the estimates of numbers like the outgassing rate?
Not so. I think this is a worst case. But you have to take the worst case. And they take other situations, and then they take the best getters, the best operation that they've demonstrated of getters, and that's not in space. They take that and they say, well, you should be able to get it down to that. Obviously, you can do much better than that if you can vent it to space without causing troubles in the original venting process. There is this pyrotechnic idea, and then there's another idea that has something to do with having a piece of metal that is already scored. And as the pressure outside becomes much less than the pressure inside, it just naturally explodes itself. That's an idea for another mechanism.
This is for opening up the spacecraft.
Right, and if you could do that, there'd be no question this could be lower.
So why does that matter so much when you're worried about several years later the outgassing?
Yeah, but if you don't have it vented, even if you put a small hole and use getters in addition, they thought, this was a European owner, said that the venting rate of a small hole that they could produce safely would just not be sufficient to get it below this value.
But I'm still confused. At the beginning of the mission, you've got the...
They'll outgas for more than 2 years.
Yeah. But why is that so influenced by the manner in which you open the spacecraft up?
No, outgassing is not. The problem is, and you'd love to open the spacecraft up, the problem is when you open the spacecraft, will you do some damage? If you open it up pyrotechnically and something comes back and it hits your telescope or your mirror and ruins the surface quality, your mission's gone. And it wasn't worth the attempt. So the question is, can you find a way to open it up safely. If you can do that, then these problems will go away. If we look back at the table, there are two that depend on pressure. This radiometric one is very small, and it's the residual gas that goes as square root of pressure that's significant. It's not the worst. It's significant. It only goes as square root of pressure, so it doesn't help that much. And laser photon, if we assume intensity fluctuations about 1/100%, which is far more than the shot noise limit, Bob Spiro went over that, it still is just a very modest contribution, about 1/30th of the whole budget. So it doesn't seem something to worry about. Thermal effects, big guy. I already explained, there's two sources of it. One is from the spacecraft, and you have this distortions in the aluminum, causing effective gravitational wave disturbances, looks like it. And then fluctuations across the housing making pressure. The radiometer effect for the change in gas pressure, check all these, seems insignificant. The thermal radiation pressure fluctuations, if I just assume Stefan-Boltzmann law and take the fluctuations in it, and I allow the fluctuations to be as small as 60 microkelvin per root hertz, maybe optimistic, but some people have asked for 1 microkelvin, I will get differential radiation pressure fluctuations on about 1/3 of our whole budget. But look at this. In order to make it 1/3, I really had to work hard, because originally it was the whole budget. And then I had to think, wait a minute, it's not all hitting normally, right? And if you remember way back in physics, that you get the energy density of a Lambertian object, the energy density in the gap is 1/3 the total energy, and you go, yeah, right. That's that integral of cosine squared theta d cosine theta. That's really important. Otherwise, I blow my whole budget. So check that. Check that and see if you believe it. The distortions from the thermal fluctuations in the spacecraft, if I assume aluminum again, CTE of about 25 micro per microkelvin. So I'll get a motion of maybe 10 to 15 nanometers per root hertz, half a meter away. That doesn't seem to be significant if I assume maybe 5 kilograms disturbing mass. And again, you can always refer to that first big table, this guy, for the assumptions. Okay, now we come to the big guys, those 5 things that all come from the sensor. And I'm only going to talk about the 3 that are killers, and I just want to give you an idea of why they are. You're welcome to check this stuff, or look in the appendix of this paper I'll let you put on your web. Because it took me a while to derive that, and it's not done anywhere else, and I'm not, well, I guess I'm sure about it, I just don't like it. So here's your little proof mass, and the electrodes around it. There's a gap on each side, nominally equal, but not quite. So nominally 2 millimeters, but there could be an asymmetry of maybe a micron. The average voltage on each side might be 1/10 of a volt, and the difference of the voltages maybe 1/100th of a volt. Fluctuations, we'd like to think they could keep them down to 10 microvolts per root hertz. Not clear, but that will be a fluctuation that turns out to be important. You can work out what the capacitance for each side, but it's about 6 picofarads. So the total capacitance, if I ignore a capacitance to ground, which I didn't draw right here, about 6 times that. If I don't let the charge build up past 1/10 of a picocoulomb, then this turns out to require discharging about once a week, at least with the data I use for charging rates. And but with a Poisson fluctuation in the charge rate, which unfortunately scales as 1 over frequency according to our data, that's a killer. That's a bummer. And every piece of data shows that. That's all from cosmic rays, so love it if you could come up with new data, but I don't think so. You can just go through the whole thing, write the total mechanical energy for all these electrodes, and then write the force as the derivative. Let's just talk about one axis of the energy. And you get electrostatic forces, you get free charge interfering with its image charges on the electrodes, and then you get the free charge interacting with the applied voltages through capacitance gradients. Trouble. The biggest one turns out to be fluctuations in the charge interacting with the difference in voltages, the mean difference in voltages across electrodes. They say that they can't go smaller than 10 millivolts in order to have any reasonable sensor sensitivity at all. And we know they can't do anything about the charge fluctuations. So here it is at almost 1/10 of our budget. And I didn't write it here, I missed that, but this should be 1 millihertz over f. So it goes like 1 over f from delta Q, always 1 over f, or 1 over nu. So this is trouble. That's the killer at 10 to the minus 5 hertz. So here's a quick summary of our disturbances. We can keep all the direct disturbances, even those from the electrostatic effects, down below half our total budget. Oops, this should be for nu greater than 10 to the minus 4 hertz, typo. And it's dominated by thermal radiation pressure, by residual gas impacts, and by this sensor effect, charge fluctuations interacting with the difference voltages. But at 10 to the minus 5 hertz, they're over the whole budget, and they're aggravated a little bit by gradients of the spacecraft field, but they're totally swamped by the capacitive sensor. And the only way to suppress this capacitive sensor effect, A13, is to widen the gap. If you look back at it, I didn't point it out to you, but it goes like 1 over d. Unfortunately, not 1 over d cubed or 1 over d squared, it's just 1 over d. That's something. If you could widen it from 2 millimeters to 4 and it cuts it to half, it still swamps the budget at 10 to the minus 5 hertz, but it's something. But the problem is, if you widen the gap and reduce the sensing voltage, which is really the only way to bring it down below our budget, you don't have a good sensor anymore. So, you're a world of hurt right there. I don't know what to do about that one. Okay, the final question, we've answered almost all of them except for that K. What is the coupling? And there are only 2 sources of this weak coupling between the proof mass and spacecraft. One is gravitational force gradients. You take a disturbing mass, maybe 5 kilograms, this is as big as anything's going to be, even the whole power unit isn't that heavy, and move it a little bit. Of course, the fluctuations in the force are going to be linear with the fluctuations in the motion. And you get a coupling of about 5 times 10 to the minus 9. Remember we said the capacitive sensors to date have never proved themselves to be better than a factor of what, 20 worse than that, 10 to the minus 7? Still, I did a theoretical analysis of what the sensor contributions to the coupling could be. And with the very, very best assumptions you could have, which is including a capacitance to ground and making it very small. Most capacitive sensors make this very, very large in order to have good sensitivity, and this factor is always 1. But in principle, you could make it as small as 1/6. So I did that. And I tried to push these down as much as I could. It made the people in Italy very happy because it wasn't looking like we were going to promote capacitive sensors. But it might be a lie. And the final one, patch field voltages, which really come in as a coupling constant, although...
You want to explain what a patch field is?
Yeah, I started to talk about it earlier. It's the variations in the work function in a metal, in gold, because the crystal structures aren't laid down perfectly. They can't be. So the variations in the work function will leave DC variations in the voltage that's there that another electrode will see on maybe 0.5 millimeter to millimeter scales. And they can be as large as 100 millivolts, maybe larger.
So these patch effects are often a major issue in high precision experimental, high precision mechanical experiments.
People at Los Alamos had to study this for one reason or another. Jordan Camp worked on this. And they had not the gold alloy that we're working with, but pure gold. I think it was like 98% gold. And very contamination-free, extremely clean. They went to great efforts to keep all the contamination done. And so a lot of this patch field voltage effect can come from contaminants on the surface. It's not all just the crystal planes. And so they managed to get this down. He thought that they could get it down to 5 millivolts. Quite a bit better, a factor 20 better than this. But then there was a very controlled condition, and it wasn't the alloy we're using. It's not clear that we can guarantee we won't have all those contaminants. It's just not clear. Plus this little factor out here in front has all sorts of things to do with whether your patches are transverse or horizontal. And if you try to take a rough average, make that number 5, which is the best I've ever seen it, when Clive Speak and others in Britain have tried to be honest about it, that's about as small as I can make this effect. But it could be much larger, and that's what's scary about it. Even so, gravity gradients are bad enough to make the coupling bad. So let's go see what this all means. We go back to these equations. We now have calculated what all these things are. The external disturbances to the proof mass in the spacecraft, The spacecraft external disturbances, we calculated those. Coupling, we just calculated. We infer from those things, well, our readout sensitivity, we know what it needs to be, but we're going to see if we can get that. And the spacecraft control loop gain, again, we infer what it needs to be in order to keep each of these three terms down to about half the LISA budget, so that when you RSS them, you're below the whole budget.
RSS,
Root sum square? Kip, I learned that from you. I'm sure I did. Oh, okay. That must be a JPL-ism.
I haven't seen that since I was designing rocket engines for faculty.
See, so I must have got it from JPL. It's a rocket scientist thing. I'm a rocket scientist. A real rocket scientist. Okay. I can almost fly a rocket. So if you take the pessimistic coupling K, with capacitive sensors, now you're talking about spacecraft control loop gains of almost 100,000, and that gets to be a little bit tougher. At any rate, though, your readout sensitivities for LISA, because it's not an accelerometer, aren't that bad. The other conclusion is that that one capacitive sensor thing will destroy the whole budget if you go to lower frequency. Well, you already saw this summary, but there's just a little bit more to add to it. The sensor sensitivity required value is set by whatever your coupling factor K turns out to be. The way I calculated it was dominated by gravitational gradients, but if you have capacitive sensing as it is now, or thought it could be now, it's going to also require that your sensitivity be about 10 nanometers per root hertz, much less than the 6 picometers per root hertz for the Gradio accelerometer, but still a challenge. Already demonstrated on the ground optically, not demonstrated capacitively under LISA's requirements. Non-capacitive sensing can certainly provide you with a smaller K, at least as small as the gravitational gradients, and it can provide a really good sensitivity. But you also need to control, initialize, and cage the thing. So it's not as though you're going to do without the electrodes forever, because I don't think you're going to cage the thing during launch and do the coarse control you need to initialize it with lasers. I doubt that. The spacecraft control loop gain, again, is set by whatever your coupling is and whatever the disturbance is on the requirement, and at all frequencies, the requirement seems to be reasonable. The only ways to push the disturbance limits down at low frequencies: one, reduce the spacecraft magnetic field gradients; active thermal control, not so hard; open to space for better vacuum, and maybe omit capacitive sensor, or find some kind of sensor that's less sensitive to charge on the proof mass. So here's some stuff to do, and now I get to some pretty new graphs that show heritage and what we're going to do. And I won't go through in detail. In fact, Bill talked about some of these. The Triad satellite in '72 was a spherical proof mass, had a 1 centimeter gap to its electrodes that were in 3 sides. It used the same, almost the same kind of alloy, heavier on the platinum. Again, as the solar flux pushed the spacecraft, it monitored, it sensed it capacitively, and fired thrusters to keep the spacecraft in one axis centered on it. It achieved about a nanometer per second squared root hertz at a millihertz. They had a problem with a 1 centimeter boom misadjustment. I believe it was this boom, and they couldn't fix it because they lost their telemetry. So that was probably their biggest cause of not doing better. And they also had liquid coal gas propulsion in a little torus around here, so there was sloshing. The torus minimized that, but they knew there would be some. I think the real problem was this accident, which you need to allow for. And of course, the usual, they had capacitive sensors, so had the, but at 10 to the minus 9, those probably weren't the driving thing. Here's what's been done on the ground. You saw this from Bill. This was done at Onera in Paris. And these are the accelerometers that went on Aristoteles. There's 2 of them. They used one just to measure the platform motion.
What was Aristoteles?
It was a gravity gradiometer mission. They wanted to measure the gravity moments of the Earth. In fact, these are the ones that are on GRACE are similar to these, but actually less.
What is GRACE?
The Gravity Recovery and Climate Experiment that just launched. Kip. Anyway, it just launched. You're just not reading your universe when it comes out every 2 weeks. Okay, I'm just teasing. But you guys should know, right? Okay. Anyway, all they got, their theoretical limit would be about a factor of 1,000 short of LISA, but they only achieved a factor of 1,000 worse than that. Again, mostly limited by seismic motion. tip, tilt, and twisting. And here, it wasn't even at a millihertz that they got that 10 to the minus 9, so it's really pushing it. And yet that's the best that's been done. And there's a pretty picture of their setup. Here's Grace. It's 2 spacecraft tracking experiments. It started out as the Geopotential Research Mission back in '78. It went through about 5 names and finally became a mission. And challenging mini payload or something, I don't know. Anyway, they use all these accelerometers, and nobody's doing better so far. Nobody's doing. This is this LISA test package, ST7. I think Bill talked about that. But this I want to go into just briefly. This is the only ground-based test that looks promising as a test of really seeing a force or acceleration down at LISA's level. And this is Eric Adelberger and his group up at University of Washington. And they were actually trying to do a test of the equivalence principle. It's a torsion balance, and they actually had 2. And they were measuring rotational noise, and they were in the LISA bandwidth. I just include these numbers so that you can duplicate this. This is a superb exercise for the student. And the underlined numbers are the only numbers I had to give you, and every other number up here you should be able to derive. They used little 10-gram copper beryllium masses out at about pi centimeters from the center. And you can guess the moment of inertia. The resonant frequency was about 1.5 millihertz, right where LISA wants to be. And the damping time for their torsional pendulum was about 3,000 seconds. You can guess the Q. It wasn't very good at 25. But what's really exciting about this is the force that they were able to measure, which was about 500 femtonewtons per root hertz, is exactly the thermal limit from your fluctuation dissipation theorem. Exactly. What does that tell you? It says that they were probably doing much better. They just couldn't, even in principle, ever see any better than that. And it's not easy to see that from the graph unless you use what you know about the fluctuation dissipation theorem to convert the force formula to an angular formula. So there it is. You can check it. And all you needed to do to get that was, I needed to tell you it was a tungsten fiber. I needed to tell you its radius and its length, and its torsional stiffness, and its rigidity, and you get all the rest of it. And so the thermal limit becomes 1/10 of a milliradian per root hertz. And sure enough, if I go to their frequency, never mind this arrow, that was just their rotating turntable. And I seem to have cut off my abscissa, but there we are at 1.5 millihertz, their resonant frequency. And there they are, 10 to the minus 2 milliradians squared per root hertz. So again, they're right at their thermal limit at the resonant frequency, which says that they actually did better. They thought that they were limited by tip and tilt coupling into other modes, but apparently they did as well as they could possibly have done in principle. So it's very promising. You notice how this is limited by the Q. So it's thought that if you used a higher Q fiber, maybe instead of tungsten, we went with some silicon fiber, like Phil Willems talked about here. And Vladimir Berginsky has looked into this and done calculations and thought that you needed a Q even less than 1 million, and you could do this. So in fact, he has an idea for it. So this is work in progress, or should be, because there is no other planning around.
So the issue here is to build a facility similar to this for testing the.
Yeah. There's no other plan or method known right now to demonstrate an ability to measure a force down this far. And since it seems possible in principle, somebody else got down to the thermal limit or below, it's probably worth doing.
You're not going to do it in Adelberger's lab?
I think it's a great idea. We're going to go up there and encourage it.
I discussed it briefly with Adelberger last week, and he's cautiously encouraging.
Does he know how important it is? How great it would be?
I think he does. It's a question of his own personal commitment. There are others in his lab that he thinks.
Yeah, you mentioned Blaine.
Blaine Hackle.
Yeah, okay.
Is quite interested.
Great.
So Connie and I and Tom Prince will go up and talk with Eric and Blaine and others sometime in the next month or two.
Yeah, it's not the kind of thing you can just set up here in somebody's lab. It really takes an infrastructure that's already there. And I'm just going to run through some pictures, some of which you've already seen, and you can use it for reference later. We talked about the thrusters on the spacecraft, so for 6 degrees of freedom, you're going to need at least 3 clusters of 2. And you don't have to have any control in the solar flux axis, because you've always got it from the solar pressure. All you need to do is act against it. Only one direction on that axis. And you have 2 for redundancy, so there they are. I'll just go through this, and I'm not, well, just questions. You already know what the solar pressure force is. The thrusters only need to combat the solar pressure force, so about 20 micronewtons is enough, and 100 nanonewtons resolution. And I think Bill talked to you about the Phys thrusters. Otherwise, you're welcome to read this stuff later. I don't want to run overtime on this stuff. Read about what they are. Here's something about the sphere versus the cube. I think Bill talked about this briefly too. There are advantages to a sphere. Maybe you could even get by with just one. So now from 12 degrees of freedom of 2 cubes, you've gone to 3 degrees of freedom on a sphere. Now get larger gaps.
Sphere to handle both.
Yeah, why not if you had a perfect surface? You could. It was the original idea that would allow larger gaps. The triad had 1 centimeter, even with capacitive sensing. Of course, you lose redundancy if you use only one sphere. And the spherical surface isn't all that smooth, and you can spin it, but that only gets you longitude, it doesn't get you latitude. And if you have an imperfect surface, you still have to articulate 1 degree per year. That's so great. It would be a great candidate for optical sensing, but how do you do the control? Back to capacitive. Maybe. Well, Tom Prince has this idea about gravitational. I'll get to it. So the cube has a smooth, plane surface, and even though it's imperfect, it's controllable. It's a lot easier to test on the ground, and there is all this heritage with accelerometers. And I stressed with accelerometers because they're not altogether relevant. Here's an optical sensor that's already been proven to demonstrate better than 10 nanometers per root hertz. And you can go up and see it in the lab at JPL anytime you want. They love to brag about it. A woman named Meng Chow is building it, but she's been under the supervision of several others there, that, many of whom you know. It just bounces out an LED off the proof mass and onto a quad diode. And all you need is 3 of them reflecting light off the little corners. So that's 2 faces at each corner, and you've got 6 degrees of freedom.
You want to explain for the theorists what a quad diode is?
Oh, it's, you let light shine it, and it's divided into 4 quadratures so that you can see very accurately if it moves this way or this way, what it's done in the axis of motion, just by where the light is hit on the diode, as opposed to having 4 different diodes. Here's a picture of it, and this is actually not the most recent data. This is 1 nanometer per root hertz, a little above that in a millihertz, but she's got this. I saw data a week and a half ago that was much better than this. I just couldn't get my computer to receive it. There's a pretty picture. This is Tom Prince's idea, and it's really cool. It's about the most uninvasive, purest, most elegant technique for control, not necessarily sensing, but for small control. I mean, after all, this is gravitational waves, so what do? You put little, I can't draw for anything, but anyway, you get the idea. This is supposed to be 14 little control masses on each face and each corner. And I envision, and this is just a first thought, that you'd put each of these on a little platform with maybe 3 piezo stacks that could move in piston, tip, and tilt. So effectively, you can move each of these control masses in 3 axes. And I just did a quick calculation, treating this proof mass as a point and each control mass as a point. And I said, if I made them 100 grams, and I put them 5 centimeters away from the center, and I moved 10 microns, and you can do the exercise because you'll find that you have to go 3rd order before you have an effect. And you have to find that sometimes you move them one way and it doesn't work. But I could get a force at least equal to 20 piconewtons. That's in the ballpark. And moving them 10 microns is well within the ballpark of the piezos I looked up. I'll show you in a second. And these are the requirements you eventually need for your proof mass. So I really hope somebody here will do the exercise and tell me which ones optimally I'd need to move, how far, or just even what would work. You don't care if you optimize it, to get this kind of linear motion or rotational motion of the proof mass. And you could actually have more control masses out here on a track for course compensation if an accident occurs, like happened on Triad. Optical sensing or maybe capacitive would be fine. You have to sense it. Well, what a great way to actuate it without imposing voltage fluctuation. So here's this idea of having a little piezo stack to use to move the control masses. And looked up on the web and found these guys, and you could stack these all you want, and they'll get all the motion and the rotation that we need. I forgot to put the website on here, but it's in a paper I did. And I just started, I gave somebody else at JPL, asked him to help me. He does formation flying. And he came back with these incredible view graphs in 2 days no equations, no numbers, but boy, can you draw a picture. So I had to include his pictures, and I'm hoping to get some equations. But you don't have to draw pretty pictures, but I'd love it if you'd do the physics and check the numbers. So here's the whole summary, and the whole thing's done. The disturbances to the proof mass from the spacecraft and the space environment are reasonably well understood and estimated, I think, but you're going to check that. To reduce them further may require active thermal control of the housing and the spacecraft. It's really the spacecraft. Venting to space for better vacuum, and I said this as discreetly as I could, sensors that are less sensitive to proof mass charge. Because it wouldn't be right to say better sensors or get rid of capacitive sensors, because all I really need, if you look at the physics, is they need to be insensitive to proof mass charge, and that says it all. The proof mass disturbances from the position sensor back action seem to be problematic under a millihertz with capacitive sensors for this reason, sensitivity to charge. And they also involve effects that are not well understood, the cosmic ray charging rates and the patch fields. Third, the methods for ground testing of the proof mass sensors and actuators definitely need development and study. They may not be possible at the required performance level, at least for capacitive sensing. New design options need to be explored carefully and soon. And the trade studies need to be done. And I can't emphasize too much soon, because if you don't come up with a really strong argument and proof that something is viable, not just the argument that it's better, but proof that it can be done, it won't become the baseline. And it doesn't matter if it's proved a year later, the baseline won't get changed. NASA wheels turn slowly. So I'd say there's about a year window to come up with any new great idea, realistically. But you also have to keep in mind that there's caging initialization and coarse actuation. So I don't think we'll throw away the electrodes. This is for you guys. There are several promising research opportunities. That's it. End of slideshow. Click to exit. What am I supposed to click?
Well, normally just clicker.
Well, you changed. Oh, there you go. Okay, I'm out. Anything you want? Any questions, or you want to see something? Ladies and gentlemen, the weather in LA is fine. Thank you for joining us for the flight.
I'm wondering, like, how much will the solar wind?
How much will the what?
How much will the observations in solar wind? The fluctuations in solar wind?
Oh, they're redder and lower, and their DC value is much lower. So it wasn't a significant contribution, but I'll show you the numbers for that. I don't have them right here. I think they're in the reference, the PDF that I'll give them to put on the web. But if they aren't, email me and I'll send them to you, because I know right where they are. No, they're much lower, about a factor of 100 lower.
I think they're larger, so they must fall off with decreasing frequency.
Yeah, at millihertz and lower, they're just not.
You go up to something like 1 hertz or so, and they become more or less comparable, I think.
They're much redder than the solar flux, and these guys go as 1 over nu to the 1/3, and I don't know if the solar wind goes as 1 over nu to the 1/3 or more steeply, but the DC value that multiplies the 1 over nu to the 1/3 is much smaller. So they didn't turn out to be an effect. I believe there's something said about that, or at least micrometeorites, in the appendix to the LISA Phase A document. Either the American one or the European one. Yes. You guys are going to get lots of homework problems. I know it. I can see it in his eye.
Well, you have to give them to me, and then I'll edit them.
I just gave them to you. Did you get them all? Right? You got them all? A13, A9. That'd be good. Thanks.